So this is another Unit 3 video from Advanced Higher Chemistry. This is going to be probably one of several videos on volumetric analysis. This one is our introduction. So what is volumetric analysis? Well, volumetric analysis means any analysis that uses volume of chemicals to determine information about them. Most volumetric analysis will involve doing titrations, and so the most common equipment you will use is a burette, a pipette and a volumetric flask. So you do need to know how to prepare a burette and how to prepare a pipette, making sure that they have been rinsed out with water and then with the solution that you're going to fill them with, making sure that there are no air bubbles, making sure that you fill them to the mark if it's a pipette, making sure that you're reading it at eye level if it's a burette, and also making sure that you never fill a burette above eye level and you use a funnel. Also, you'll use volumetric flasks to prepare standard solutions. So there's some terminology that we need to know, and this video will actually go through all 5 of these. So this is just going to be terminology. We have concordance, endpoint and indicator, which are very quick, easy things to go over. A lot of those are just going to be revision from Nat 5. And then standard solution and dilution, we're going to go beyond what you know from higher and explain in a bit more detail and involve some calculations when it comes to dilution. So firstly, concordance. When you do a volumetric analysis, you want to make sure, as with every experiment, that your results are reliable. So you're going to repeat your experiments. Your results will be considered reliable if your final volumes that you're obtaining are within 0.2 milliliters or centimeters cubed of each other. And we describe such results as concordant. The ideal circumstance would be that your results are identical to one another, exactly the same. But concordance is good enough. When you are working out an average, you will only ever use your concordant results. So if you have a result, if you have a table of results and there are like 4 results, one of them is not concordant with the other ones, you just would not use it to calculate an average. The endpoint. Well, the endpoint of a volumetric analysis is when you know the reaction is finished. There's usually a visible sign that lets you know that the reaction is over. And an endpoint can be categorized usually by a significant change in a value such as pH or conductivity. So it'll either jump to a much higher value than it had been during the experiment or drop to a much lower value. And if it's not a change like that, then it's usually a color change. And many volumetric analyses will use chemicals designed for specific reactions that will change color at the end point, and we call these indicators. So indicators are used to reveal the end point for reactions where everything's the same color or everything's colorless. Indicators must be appropriate to the reaction being done. So there's no point adding an indicator that's not going to change color at the specific endpoint. So if you know the pH of the endpoint of a reaction for an acid-base titration, you can choose the best indicator. An indicator that changes color at the pH range at which the reaction ends is what you are wanting from page 14. A specific indicator, if iodine is involved, would be starch, and starch goes blue-black when iodine is present and should be colorless when it is not. There are reactions that naturally change color, and we describe those ones as being self-indicating. Many titrations involving the formation of transition metal complexes or redox will be self-indicating and therefore won't need an indicator. Now we're getting into standard solutions. Now, a standard solution is any solution that we know the exact concentration of. And there are 5 steps that you need to be able to describe when preparing a standard solution. First thing is you need to weigh your standard, and we'll talk about more information about what sort of chemicals can be used as standards in future slides. Once you've weighed your standard, you're going to dissolve it in a small amount or a small volume of distilled or deionized water in a beaker. The reason we dissolve it is because liquids are much easier to transfer than solids. You're going to transfer your solution from the beaker into a volumetric flask, and you're going to rinse that flask out a few times with deionized or distilled water to make sure that any solution has been fully transferred into the volumetric flask. You're then going to make it up to the graduation mark of the measuring cylinder. Remember, that means the bottom of the meniscus is touching the graduation mark. Then you stopper it and you invert it, which means you turn it upside down and back several times to mix it. And that is how you prepare a standard solution. Now, not every chemical makes a good standard immediately. The chemicals that are suitable for just dissolving and being able to say that you know the concentration after doing that are called primary standards. And primary standards must meet this list of requirements. So you must be able to buy them in high purity. So that means being able to purchase it in high purity and trust that it's not absorbing anything like water when it's left to sit, which is an issue with quite a few chemicals. So it must be pure. It needs to be stable as a solid for whenever you're storing it, and stable in solution after you've dissolved it. It needs to be soluble. There are lots of chemicals that are not soluble, therefore you can definitely not make standards out of them. And finally, you want to have a reasonably high GFM. Now, the reason for this is the higher the GFM of a compound, the much smaller the error is if you make a mistake in weighing. The higher the GFM, if you are out by a few milligrams, it's not really going to affect the concentration that much. But if you've got something with a really low GFM, even a small difference in weight compared to what you wanted, from what you wanted compared to what actually made it into the flask, will have a significant effect on the concentration. So the higher the GFM, the smaller the effect of mistakes in weighing will be. Now, this is a list of good primary standards. If you're watching this with your summary notes, these are all included in your summary notes. But we have things like sodium carbonate, hydrated oxalic acid, silver nitrate, potassium iodate, potassium dichromate. Additionally, when it comes to acids like hydrochloric acid, sulfuric acid, etc., you can purchase pre-made standards that you can use directly. Now, anything that is not a suitable primary standard can still be made up in a volumetric flask, but we will consider it a secondary standard, and something that we will actually need to prove its exact concentration. So you make this solution as normal, but you then need to do a titration of that chemical against a primary standard to determine its exact concentration, and then you can use it knowing what its exact concentration is. So one example of a chemical that we would really want to use in lots of titrations is sodium hydroxide, but sodium hydroxide has a low GFM, and it also absorbs water when stored as a solid. So it's not very good for use as a primary standard. So it is a secondary standard, and what we usually standardize it against, what that means is standardize against means what primary standard would we use, is we would use the hydrated oxalic acid. So we do a neutralization. The last thing is dilution. Now, if you have a standard solution prepared, you can use it to make other standard solutions of lower concentration by diluting it. Now, the process of dilution is better than making up every standard from scratch because there are less sources of errors and because you're working with liquids, which are easier to transfer than solids. Additionally, because you are diluting it, you're lowering the concentration. Any errors you make also get diluted out by doing a dilution process. So in fact, you're making your solutions more accurate by doing dilution. There are two types of dilution. Serial dilution. Serial dilution is mostly used in biology. It's less common to use it in chemistry. The only time that you would use serial dilution really is for changing the pH of solutions. Now, what you do in a serial dilution is you have one stock solution, one stock standard solution, and you take usually 1 milliliter of it and then you add 9 milliliters of water to it. So you've diluted it by 10 overall. Then that second solution, you do the same thing. Take 1 milliliter of it, add 9 milliliters of water. You've diluted it by 10 again, and then you can repeat that process. Now, the reason we would use 10 as a dilution factor in chemistry is when you dilute an acid or an alkali by 10, you're changing the pH by 1. Every 10-fold change in acid concentration or alkali concentration changes the pH by 1. If you're diluting an acid, that would be raising the pH by 1. If you're diluting an alkali, it would be lowering the pH by 1. The more common type of dilution that we would use in chemistry is an individual dilution. And this is where you have a stock solution, and rather than wanting to make a series of solutions that all are related to one another by the same factor, you might only need to make up 1 or 2 solutions that have very specific concentrations that you want to make. And to do this, we use our dilution formula. And it's C1V1 equals C2V2. Now, always in this, what we're working out is V1. So C1 is the concentration of your stock solution, your standard solution. C2 is the concentration you want your diluted solution to be. Remember, because you're doing a dilution, C2 always has to be lower than C1. V1 is what you're working out. It's how much of your stock solution are you going to need to add to your flask in the second one. And in order to know how much you're going to need to add, you need to know what volume your final solution is going to be, and that is V2. So you need to know your starting concentration of your stock solution, what concentration you want your diluted sample to be, and the final volume or the container size that you are making up your final solution in. Then you can use this formula to work out how much of the first solution you need to add to the flask and then top it up with water. So I've got a worked example here. What volume of 2 molar nitric acid is needed to make 250 mils of 0.1 mole per litre solution of, well, that should say nitric acid because it still should be the same acid. So nitric acid and nitric acid. So what we do is read from the question. Our nitric acid is what we're starting with. It's got a concentration of 2, so C1 is 2. V1 is always what we're working out. C2 is our concentration of our diluted solution, which is 0.1, and the volume is 250. It actually doesn't matter. You could convert that into litres and it would give you V1 in litres, but if you have it in millilitres, it'll give you a V1 in millilitres. You do not need to convert it. Just know that whatever the units of your volume on one side are the same units of volume on the other side. So when we do this, V1 would be 0.1 multiplied by 250 and then divide by 2, which gets us 12.5 millilitres. So if we want to make up that individual diluted solution, we would need a pipette to add 12.5 millilitres of stock solution from bottle 1 into our 250 millilitre flask, and then we would top it up to the graduation mark with deionized water, stopper it, invert it, and we know we would have a 0.1 mole per litre solution. So that has been our introduction to titrations. Future videos will look at some specific examples of titrations, different types, and also do some worked examples of experiments that use titrations.